Video, it's basically going to be solution concentration boot camp. So in prior videos, we did an example 1A, and we also took a look at 1B. Now I'm basically just going to go through every single problem. You don't feel like you need to watch every one. If you look at the description on YouTube, I kind of will have a bookmark for each problem. So I'm just going to take it one problem at a time. I will even do the optional one. So in problem 1C, they ask us for what the molality of the sugar water is. So again, at the end of every problem, we want to write down the units that we're looking for. And molality, if you take a look up at the definition, would be moles of the solute, which in this case would be the sugar, divided by not the liters of solution, that would be molarity, but it would be the kilograms of the solvent, which would in this case be the water. So what do we know about those two values from this problem? Well, I don't know the moles of the sugar, but I do know that I have 4 grams of sugar. And I don't know the mass of my water, but I do know that I have 350 milliliters of it. So I can easily go back and fix both of those. Probably the easiest one to fix would be the sugar. So we know we're going to have to cancel the grams of sugar. And we're going to go to moles of sugar. So from this problem, it tells us that 1 mole of sucrose weighs 342.34 grams. So in this case, the 342.34 grams goes on the bottom. And that's 1 mole of sugar on top. So that is what we want at the end of this problem. That and that cancel out. So we're almost done with this problem. We just have to change milliliters into kilograms. Well, kilograms is mass, milliliters is volume, so hopefully you recognize that that's just a density problem. So we need to cancel milliliters. We'd like to go to kilograms, but I doubt they'll give that to us. And it says the density of the water is 0.975 grams per milliliter. So 0.975 grams for 1 milliliter. And then we can simply go back and change it to kilograms. So milliliters is gone. Milliliters is gone. So right now I have grams of water. And now that I'm pretty much right at the end of my problem, let me clean this up a little bit. Our last step is going to be changing that grams of water into my kilograms of water. So on the back of the periodic table, it tells you that a kilogram is a 10 to the third gram. It's a lot bigger than a gram. Cancel that out, cancel that out. So now we are pretty much ready to solve this problem. So I'd like to estimate before we do that. So 10 to the third on top is about 1,000. 1,000 divided by 342, well, that's close to 333. So 1,000 divided by 333 would be 3. 3 divided by 0.971 is basically 3 divided by 1. 3 times 4 would be 12. So now I basically have an answer 12, about 12 divided by 350. So I could do a 300 and I could say it's about 12 divided by 400. It's going to be somewhere in between both answers. So 12 divided by 3 would be 4. And then I'd have to divide it by that 100, so make it 2 powers of 10 smaller. So I think the answer is close to 0.04. Doing it this way, 12 divided by 4 would be 3. And because it's 400, I'd make it a power of 10 smaller and a second power of 10 smaller. So I think the answer is probably pretty close to 0.035, which if you look at the answer key, that's a pretty good sign right there. But let's chuck it in the calculator, see what we get. So we're going to take 4 on top, divided by 350, divided by 342.34. We don't have to multiply by ones on top. We'll also divide by 0.975 on the bottom and multiply by 10 to the third, which is 1,000. And sure enough, when I do this problem, I get 0.034239679. Significant? I don't think so. So then, let's talk about sig figs. We multiplied and divided. There's 3 sig figs there, 3 sig figs there, 5 sig figs there, 3 sig figs there. It looks like the least number would be 3. So 0.03424 would definitely round to 0.0342 moles per kilogram of water. So sure enough, we got it right. All right, now we're going to take a look at the next problem, which is part D. What is the concentration of the sugar water in parts per million? So parts per million, if you look at the definition, it's kind of like percent, but rather than parts per hundred, it would be parts per million. So 1 part and 10 to the 6th parts on the bottom. So whatever that part is, it could be grams divided by grams. It could be milliliters divided by milliliters. I think probably the easiest way to do this problem would be just to leave it in grams, because when we did problem 1b, we have 1.16%. So, and that's by mass. So it would be 1.16 grams of sugar for every 100 grams total. So now the only thing we have to do is we have to scale that up to 1,000,000 on the bottom. Well, to do that, we're going to multiply by 10 to the 4th, because 10 to the 2nd, 10 to the 4th would be 10 to the 6th. And if I multiply by 10 to the 4th on the bottom, we'll multiply by 10 to the 4th on the top, or make it 4 powers of 10 bigger. So I get 1, move it once, move it twice, move it 3 times, move it 4 times. I think the answer is 11,600 divided by 1,000,000, or 11,600 parts per million. So the cool thing is it's basically like a percent, except it's scaled up by a factor of 4, a power of 10 of 4. All right, so that is problem number 1. Let's go ahead and take a look at problem number 2. I know we went over this in class, but just in case you need to see it again, molarity is going to be moles on top. Moles of our solute, which in this case our chemical is HCl, and we're going to divide by liters of solution. So let's go fishing for what we know in this problem. Do we know anything about HCl? And sure enough, it has a molar mass of 36.46, but how much did we actually dissolve in this problem? 27.3 grams. So 27.3 grams of HCl, and we dissolved it in 125 milliliters of solution. I think the easiest way to fix this problem is just to get rid of the milli, because I want liters of solution, but to get rid of milli, you'll have to replace that with what it represents. My pen's dying here. 10 to the negative third. Okay, so then we're in liters of solution on the bottom. We just have to fix the grams on top. So we have grams of HCl, and we want to go to moles of HCl. And if you look right here, it says 1 mole of HCl has a mass of 36.46. 1 mole, 36.46 grams. And that just came from the periodic table. I added up 1H, 1.01 grams. I added up 1Cl, 35.45. And that's where 36.46 came from. Grams cancels. So how would we estimate this problem? Well, 27 is pretty close to 30. 36 is pretty close to 40. I'm thinking the answer is about 3/4, or 0.75. This 10 to the negative third we can put on top as 10 to the positive third. So that's going to make this 3 powers of 10 bigger. 1, 2, 3. I think the answer is going to be pretty close to 750. And then we're going to divide by the 125. So how many times does 125 go into 750? Well, 700 divided by 100 would be 7. It's probably 5 or 6, somewhere in that ballpark. So let's go ahead and get our real calculator answer now. So we've got 27.3 on top. We're going to divide that by 125. We'll multiply by 10 to the positive third. Stop and get an answer. Divided by 36.46. Final answer is 5.990. 3 sig figs on top, 3 sig figs on the bottom, 4 sig figs on the bottom. Yeah, we'll go with 3 sig figs. So 5.99. Sure enough, that is the correct answer. All right, let's go ahead and take a look at problem number 3 now. A very similar problem. We want molarity, so moles on top, and the chemical we're dealing with this time is NH3. And liters of solution on the bottom. So what do we know about NH3? Well, it contains 252 grams. So we can put that on top, 252 grams of NH3. And do we know how much solution that has? Well, it is per 1 liter. Well, that's nice because we need a liter of solution on the bottom. So we're even closer to being done with this problem. If I knew how much NH3 weighed per mole, we could solve this. Well, you could go to the periodic table, 14.01 plus 1.01 times 3. So we're talking about, what, 17.04? And sure enough, it tells you it has a molar mass of 17.04. So we want to cancel grams of NH3. We want to go to moles of NH3 because that's what our roadmap says. 1 mole is 17.04. And so now we basically have to take 252 divided by 17. Well, I could make that a little bit easier. I could say 25 divided by 1.7, which that's pretty close to 2. 25 divided by 2 would be about 12. So, yeah, it's probably a little bit bigger than 12, maybe 13 or 14. Sure enough, the answer key would agree with that. But let's chuck it in the calculator. 252 divided by 17.04. Sure enough, gives you 14.78873,239. Significant? I don't think so. So 3 sig figs on top, 4 sig figs on the bottom. We'll go with 3 sig figs, so 14.8. All right, now we'll start working on problem 4A and 4B. So again, I believe we reviewed these in class, but just in case you need to see these two again. So we're talking about rubbing alcohol, and it wants to know the molarity of the rubbing alcohol. So at the end of the problem, we better have moles of the rubbing alcohol divided by liters of solution. So if we take a look at this problem, I have a lot of densities. I have the density of the alcohol. I have the molar mass of the alcohol. That's probably going to come in handy. So if I know the mass of this alcohol, I could probably change it to moles. I've got another density and another density. Well, it doesn't seem like we have a lot to go off of here, but it's oftentimes the tricky part to this problem is people forget about the 70% by volume. That is a concentration. So because molarity is a concentration, and because 70% by volume is a concentration, I think that would be a great place to start the problem. So if you didn't realize that 70% could be written as a fraction, you might have had a hard time with this one. So 70% is 70 out of 100. Because it's by volume, we have a choice. It could be liters over liters, or it could be milliliters over milliliters. It doesn't really matter which we choose, but because in the end we want liters of solution on the bottom, I might just pick the liter option. So 70 liters of rubbing alcohol divided by 100 liters of solution. So the nice thing is we're already done with the bottom of the problem. Now we just need to get the top into a format that we can deal with. So we want that to be in moles, which again, if I can use the molar mass to get it to grams. So at this point we need to go from a liters into a mass. Well, how do we go from liters or volume to mass? Well, that would be a density. So we want to cancel liters and we want to go to grams of rubbing alcohol. So there's three densities in this problem: the density of water, the density of the solution, and then the density of the alcohol. So this is the density we're going to want to use, 0.785. Now notice how it says per 1 milliliter. So I want to get rid of liters, but I have to somehow make that milli disappear. So we can make it disappear by replacing it with 10 to the negative third. And if you don't like that 10 to the negative third on the bottom, you can simply put that 10 to the positive third on the top. So now my liters of rubbing alcohol, I probably should have written that there, cancels. And now I'm in grams of rubbing alcohol. So if I could cancel that grams of rubbing alcohol with moles of rubbing alcohol, we'll be done with this problem. So sure enough, if you add up all the elements in isopropyl alcohol, you would get a molar mass of 60.10. And that's 1 mole. Grams cancels, gram cancels, I have moles. So now we're basically done with this problem. So let's do a little bit of mental math here. So we've got 0.785 times 1,000, so that would be 785. That might be a little bit easier to do as 800. So 800 divided by 100 would be 8. 8 times 70 would be 560 ballpark, divided by 60. So chop off a 0, chop off a 0. I think the answer is about 56 divided by 6, which that's about an answer of 9. So answer key agrees with that, but let's prove it to ourselves using the calculator. So we've got 70 divided by 100 times 10 caret 3. I always like to hit enter after using exponents just so my order of operations don't get messed up. So at this point I'm at 700 times 0.785 divided by the 60.10, and sure enough I get 9.143094842. As far as sig figs go, 70%, those are just kind of whole numbers. I'd go with the 0.785 has 3 sig figs. 60.10 has 4 sig figs. So yeah, let's go with 3 sig figs, 9.14. All right, well, then let's go ahead and take a look at problem 1b. Same problem, just a different concentration, or a different unit of concentration. So percent by mass. Again, we always want to start out the problem by thinking where we want to be at the end of the problem. So percent would be a fraction, a part divided by a total, and because it's mass, we'll do grams. So I want grams of the rubbing alcohol, and we want grams of solution, and at the end, once we have that fraction, we'll multiply by 100. All right, so do we know any of these grams? No, but we do know the percent by volume, so that would be a great starting place again. So we've got 70 out of 100 rubbing alcohol and solution. Now again, we could go with 70 liters over 100 liters, or because we're going to want to convert that to grams, and because most of our, all of our densities are in milliliters, I think it would make more sense to put everything in milliliters. 70% is going to be the same whether it's 70 liters over 100 liters or 70 milliliters over 100 milliliters. So I think this would maybe just be a little bit easier. And now I'm going to have to convert both of those milliliters into their respective grams. So I'll fix the top first. We'll put milliliters of rubbing alcohol on the bottom. And we'll want to go to grams of rubbing alcohol on the top. And it's really important that I recognize that it's the rubbing alcohol or the isopropyl alcohol, because that's the density we're going to want to use. 0.785. And that's grams per 1 milliliter. Milliliters cancels. I'm halfway done with this problem. Now we'll do the other one. This time we want to cancel milliliters of solution and go to grams of solution. Well, which one of these densities applies to that? We already used the 0.785. 0.997 is the density of water. My label tells me that the solution density is 0.878. And that, because that's grams, that goes on the bottom. 878 grams per milliliter. Milliliters of solution is gone. So I've got a grams on top, I've got a grams on the bottom. That's a fraction. How do you turn a fraction into a percent? You multiply by 100. So we're ready to estimate now. We can make our job a little bit easier if we simplify. 100 divided by 100 cancels. So now we basically have to do the decimals. 0.785 is pretty close to 0.8. And 0.878 is pretty close to 0.9. We could just make these a power of 10 bigger, so 8 divided by 9. I think I taught you the trick earlier in the year that a number divided by 9 would be that number repeating. Well, that's pretty close to 0.9. 0.9 would be 90%. So now I basically need to take 90% or 0.9 of the number 70. Well, that might be hard to do, but 90%, the opposite of that, or the leftover percent, would be 10%. I can easily multiply by 10% in my head because it's simply dividing by 10. So 10% of 70 would be 7. So if I take away 10% or 7, I'd be left with 90%. So 7 off of 70 would be about 63. So I think the answer is pretty close to 63%. Based on mass, so m over m. Sure enough, the answer key really likes that estimate, but we can chuck it in the calculator just to be safe. So we have 70 times 0.785 divided by 0.878. And sure enough, I get 62.585. We'll go with 3 sig figs on top, 3 sig figs on the bottom. Again, I'm not really counting the 70% as sig figs. That's just kind of a whole number. Maybe I should include that with as only 1 sig fig, but I'm going to go with 3, so I think 62.6% is appropriate. And sure enough, that's what we got. All right, let's take a look at the optional one now, the molality. So again, I think it's always helpful to write the definition. At the end of this problem, we better have moles of our isopropyl alcohol, and we're going to divide by, in this case, the kilograms of the solvent, which is water. So it says, assume that adding the volume of the solvent and the volume of the solute and the solvent gives you a total volume. That's not always a safe assumption, but in this case, I think it's pretty good. So if it's 70% volume isopropyl alcohol, it means it's probably 30% water. So if it's 70 milliliters isopropyl alcohol, it might not be the safest assumption that it's probably 30 milliliters of water. Because again, when you add liquids together, there's hydrogen bonding and everything else. It might not always add up to 100. But I'm saying you can use that assumption here. So we know how much water we have now. And we know how how much total solution we have. So I would say let's just take this answer up here, and we'll come down here. We'll bring that down here. Rather than starting at the very beginning of the problem, why not start there? 9.14 moles of isopropyl alcohol is 1 liter of solution. Okay. Well, the problem is I don't want solution, I want water. Well, if we use this ratio right here, you could say 1 liter of solution, or 1,000. Yeah, you could say 1 liter of solution, or 1,000 milliliters. 30% of it is water, so that would be 0.3 liters of water. So it's based on this simple ratio over here. Now I need to get that to kilograms. Well, I know the density of water is 0.9. Oops, I want to cancel liters of water and go to kilograms of water. Well, from up top, I know that it's 0.997 grams of water per 1 milliliter. And this isn't exactly what I want, so if I wanted to cancel that liters, I could cancel that with this liters, but I'd have to get rid of million, make it 10 to the negative third. So now that liters cancels that. I'm left with grams on the bottom, but I really need that to be in kilograms, so we'll just do one extra step here. Let me clean this up a little bit. And we'll put grams of water on the top. And we'll put kilograms on the bottom. And sure enough, if you look it up on the back of your periodic table, a kilogram is a 10 to the positive third grams. Grams, grams. And we're done. So if we simplify a little bit, we can definitely combine 10 to the negative third and 10 to the positive third. A thousandth of the number 1,000 is 1. So that simplifies. What else do we have here? We have 9.14 divided by 0.3. Well, that's dividing by 3/10. So dividing by 3/10 is the same thing as multiplying by 10 over 3. So 9 divided by 3 would be 3, times 10 would be 30. 30 divided by 0.997 is basically 30 divided by 1. So yeah, I think the answer will be pretty close to 30. And sure enough, that's what the answer says. So let's just plug it into our calculator here. We have 9.14 divided by 0.3 divided by 0.997. And sure enough, we get 30.56. With 3 sig figs, we'll go at 30.6. So this is one way to solve it. This is probably the fastest way to solve it. You could totally start out with the 70 milliliters of isopropyl alcohol and the divided by 30 milliliters of water, and then you could like start all over again. But I like starting with this number because we already knew the moles of isopropyl alcohol. All right, last thing we need to do is the parts per million problem. So one way you could do that would be to start with, so parts per million would have parts divided by a million, 10 to the 6th parts. And as long as those parts are the same, you could have grams on top divided by grams on bottom. You could do milliliters on top, milliliters on the bottom. So I like starting with the percent by mass problem. So percent by mass, 62.6%. That is a part problem. So 62.6 grams of isopropyl alcohol divided by 100, 62.6% grams total. So that is parts. Now it's not out of a million. So if you multiply by 10 to the 4th and multiply by 10 to the 4th, that'll fix that. So we'll get 10 to the 6th on the bottom. And we'll get 62. Move the decimal once, twice, 3 times, 4 times. You'll get about 626,000 over a million, or 626,000 parts per million. Now, I have a slightly different answer here. I'm wondering if maybe I went... You could potentially do parts per million based on moles and get a slightly different answer. If you went with the volume, 70% by volume, that would be 70 milliliters divided by 100 milliliters total. Again, you would do the same thing, 10 to the fourth, 10 to the fourth. That way you would get 700 parts per million. 700,000 parts per million. So either way, it's somewhere between 600,000 parts per million and 700,000 parts per million. Multiple ways to do it, slightly different numbers depending what format you're measuring the parts per million in. But we're not going to argue once we're up in like the 600,000s. All right, so that's question number 4. They're telling us that the toxic level for lead would be 15 ppb, or parts per billion, which, according to the definition, that would be 15 grams of lead over a billion grams of solution. And we have to somehow convert that into moles per liter, because that's what molarity is. So let's go ahead and just remind ourselves of that at the end of this problem. We better have moles of lead, and we better have liters of solution. So let's go ahead and start out with what we know. It is 15 grams of lead, and it is a billion grams of solution. So I got to turn the top into moles, and I got to turn the bottom into liters. So let's go ahead and fix the top. Grams of lead and moles of lead. Well, this is pretty easy. On the periodic table, I probably didn't need to tell you this, but on the periodic table, lead, element 82, is 1 mole is 207.20. Grams cancels. You're in moles, which is exactly what you want. And now we got to get rid of grams of solution and turn it into liters. Well, that's a mass to volume problem, so I need to know the density of that solution. And it doesn't tell us what the density of the solution is, but because it's so dilute, because it's only 15 parts lead, it's going to basically, out of a billion parts water, yeah, it's basically going to have the same density. So we can use this density. So 0.997 grams of solution, which I realize it's actually water, but it's close enough, would be 1 milliliter of solution. Last thing we have to do is make that milli disappear so that we get just liters. Easiest way to do that is replace it with 10 to the negative third. If you don't like that 10 to the negative third on the bottom, you can move it to the top. And now it's time to estimate, because all of our units are exactly what we want. So I'm going to take 1,000 times 0.997 and basically get 997. So that's basically 1,000. 1,000 divided by 200 would be about 5. 5 times 15 would be, what, 75? 5 times 15, 25, carry the 2. Yeah, 75. So it's 75 divided by 10 to the 9th. Well, I can't do that in my head, but I can move that 10 to the 9th to the top and make it negative. So I think the answer is 75 times 10 to the negative 9th moles per liter, but in proper scientific notation, I should probably write that as 7.5. So I had to move it 9 places to the left from 75, but if I put it at 7.5, now I only have to move it 8 places. So I think the answer is 7.5 times 10 to the negative 8th, and that would be moles of lead per liter of solution. Take a look at the answer key. Ooh, I'm liking that answer. 7.2 times 10 to the negative 8th. Yeah, that's definitely close enough to correctly guess the right multiple choice answer on a big college test. But let's go ahead and plug it in. So we have 15 divided by 10 caret 9. I'm going to go ahead and hit enter just so I don't have to worry about orders of operation. We'll divide by 207.2. We'll multiply by 0.997. And we'll multiply by 10 caret 3. Sure enough, my calculator says 7.21, let's say 8 times 10 to the negative 8th. And 15 would have 2 sig figs. Yeah, we'll go with 7.2 times 10 to the negative 8. All right, in the next problem, part B, it's a percent by mass problem, which is going to be pretty easy once we see why. Percent by mass is just parts over parts by mass. So the grams of lead divided by the grams total. And then we'll multiply by 100. Well, I already know what the grams of lead and the total grams is. So it's 15 grams of lead divided by 10 to the 9th grams total. So that is the definition of like a fraction by mass. So now all we have to do is multiply by 100. So 100 on top, 10 to the 9th on the bottom. 2 powers of 10 are going to cancel out 2 of those. So we'll get 10 to the 7th on the bottom, which we could move that to the top and make it 10 to the negative 7th. So I'm thinking the answer is 15 times 10 to the negative 7th percent. But because this is 15, I should probably make that 1.5. So I had to move it 7 places to the left from here. So now I only have to move it 6 places to the left from 1.5. So I think the answer is 1.5 times 10 to the negative 6th. And that would be percent but based on masses. And I didn't really even do any estimating here. I just cleaned up my powers of 10. So that is going to be the calculator answer. 1.5 times 10 to the negative 6 based on mass. All right, let's wrap up part C. And we'll be done with problem 5. So it says, what is the molality? Well, now I need moles of lead on top, and I need kilograms of water on the bottom. So, how do we want to go about this? Well, I know how much lead I have. I have 15 grams. And I know that's over 10 to the 9th grams of solution. And if it's 10 to the 9th grams of solution, that would really be 10 to the 9th minus 15 grams of lead. So then that's basically going to give me my grams of water, because the water is made, the solution's made up of both the lead and the water. Now, if you take a billion minus 15, you're basically still at a billion. So I don't know if that's going to be significant or not, but the mass of the water on the bottom would technically be 10 to the 9th minus 15. Then all we have to do is change that grams of water into kilograms of water. And we know kilograms is 10 to the positive third. So now that grams of water will cancel. Last thing, we have to get our lead into moles. So we'll cancel grams of lead, just like we did in the part A. Go to moles, and 1 mole is 207.20. So I'm not sure if my answer key accounted for the fact of subtracting that 15. It's probably not going to be significant. But if we take 15 divided by parentheses 10 caret 9 minus 15, because again, that's how much water we would have used. Get an answer. Multiply by 10 caret 3. Divide by 207.2. And we should get an answer about 7.2 times 10 to the negative 8th. Yeah, 2 sig figs is probably good enough here. So 7.2 times 10 to the negative 8th moles per kilogram of water. And sure enough, that's exactly what we got. Now, just to prove it to ourselves, what would we get had we not included that 15 grams on the bottom? So you'd have 15 grams on top, divided by the 10 caret 9 on the bottom. And then, what did we have to do? So that would be grams. Oh, we had to convert to kilograms. So we multiplied by 10 caret 3 on top. So that would be kilograms of water on the bottom. Oh, yeah, then we had to divide by 207.2. So either way, you're going to get 7.2 times 10 to the negative 8th. Doing it the first way is a little bit more accurate, but again, with only 2 sig figs, that 15 was meaningless. Either way, you're going to get 7.2 times 10 to the negative 8th. 6, we're taking a look at the amount of cholesterol in your blood. High cholesterol is generally not a good thing for health, and we want to know what is the molarity of that. So at the end of this problem, we're going to want to know how many moles of cholesterol we have per liter of solution, which in this case would be the blood. So let's see if we know something about this problem. It says we have 1.6 grams, that would actually be milligrams, of cholesterol per a deciliter of blood. And we know that cholesterol has a molar mass of 386.67 grams. So if we can get this milligrams into grams, then we could convert to moles, and all we have to do is get rid of deciliters and go to liters. So I think the easiest way to get rid of these metric prefixes would just be to replace them with their powers of 10. So milli is 10 to the negative third grams, and a deciliter is a tenth, or a 10 to the negative 1 liter. Oh, blug. I'm not sure what blug is, but let me get my eraser. Blood. There we go. So now I'm in grams of cholesterol, so I can cancel that. Grams of cholesterol, and it says that 386.67 grams is 1 mole of cholesterol. Cancel, cancel. So I'm in moles of cholesterol, which is what I want. I'm in liters of blood, which is what I want. So now we're ready to solve this problem. So we can cancel 10 to the negative 1 on the bottom and change this to a 10 to the negative 2, which would make that 100 times smaller. So now we're talking about basically 0.016 divided by 386.67. So I'm just thinking how I want to estimate this. So this is basically 400, and this is basically 0.02. Alright, so we could probably estimate this. If we divide the bottom by 4, that would be 100. If we divide the top by 4, that would be 0.005, I believe. Yeah, so yeah, we're talking about 0.005%, or let's see here. The top is 5 times 10 to the negative third, and then we're going to divide by another power of 2. So I'm thinking the answer is about 5 times 10 to the negative fifth. That's pretty good based on what the answer key is showing. But let's go ahead and just plug this into the calculator just to be safe. So I've got 1.6 times 10 to the negative 2. I've reduced the bottom. So yeah, we just have to divide by 386.67. And my calculator shows 4.14. Let's see here, that was a 1.60, so that would give me 3 sig figs on top. I've got 5 on the bottom. Yeah, we'll go with 3 sig figs, so 4.14 times 10 to the negative fifth, and that's exactly what we got here. Great. So let's switch to problem number 7 now. Now we're talking about blood sugar levels for people with diabetes. And this often occurs if the blood sugar drops below 55 milligrams per deciliter. So again, a very similar problem. Switch to a different color here. So we know the concentration is 55 milligrams of sugar per 1 deciliter of blood. And at the end of this problem, we want moles of glucose per liter of blood. So same sort of thing. We need to get rid of these prefixes. So 10 to the negative third, 10 to the negative 1, cancel, cancel, 10 to the negative 2. So now that I'm in grams of sugar, I want to cancel that. And we can go to moles of sugar. And because glucose has a molar mass of 180.18 grams per mole, that cancels, that cancels. I'm in moles of sugar, I'm in liters of blood. So very similar problem. Let's go ahead and reduce this. So 55 times 10 to the negative 2 would be 0.55 divided by 180. That's pretty close to 200. So 0.55 divided by 2 would be basically 0.25-ish, maybe 0.3. So about 0.3. Having a hard time getting a decimal point there. There we go. 0.3. And then we still have that 100 on the bottom times 10 to the negative 2. So I'm thinking the answer is 0.003 moles per liter, or 3 times 10 to the negative third. So let's check this in the calculator, see what we get. We have 55 times 10 caret negative 2, get an answer, divided by 180.18. So sure enough, with 2 sig figs on top, 5 on the bottom, we'll go with 2 sig figs, so 0.0031. Or 3.1 times 10 to the negative third. Good to go on number 7. All right, let's take a look at problem number 8. So same problem here, but now we're talking about hyperglycemia, so too much sugar in the blood. So we're basically going to repeat the same procedure as the last two problems. So we know the concentration is 180 milligrams of glucose per deci my pen's having a hard time here. There we go. Per 1 deciliter of blood. Going to switch to a different pen. Good. So same thing. We need to get this into moles per liter at the very end. And because I know that the molar mass is per 180.18 grams per mole, we simply need this in grams. So 10 to the negative third. Deci is 10 to the negative 1. Because again, that'll give me liters of blood. Cancel 10 to the negative 1. 10 to the negative 3 goes to 10 to the negative 2. Now that I have grams of glucose, we can cancel grams of glucose on the bottom with moles of glucose. And it is still 180.18 grams per 1 mole. So with that last unit conversion, I've got moles per liter. So now we need to do a little bit of cleaning up. 180 times 10 to the negative 2 would be about 1.8 divided by, oh, this is kind of nice, 180. So 18 divided by 18 would be, so basically be 1/100th. 18 divided by 18 would be 1. This is not 18, but it's 180, so 100. Yeah, that looks good. So it's probably 0.01. And yep, that's looking good there. According to the answer key, chuck it in the calculator just to be safe. 180 times 10 caret negative 2 divided by 180.18. 2 sig figs on top, 3 down below. I get 0.00999, but with 2 sig figs, that would be 0.010. Sure enough, that is the correct answer. All right, let's switch gears and take a look at problem number 9. We have the EPA drinking limit. This is going to be a very similar problem to what we did with the lead problem, which was problem number 5. But now we're dealing with cadmium. So we have 5 parts per billion, which it's helpful to write that as a fraction. So we have 5 grams of cadmium over a billion parts of solution. And we need to write that as molarity. So we need to switch the top to moles, and the bottom needs to be in liters. So let's fix that top part. The good thing is the periodic table gives us the molar mass of cadmium, which is 112.41, which is 1 mole of cadmium. We're done with the top part. That is the units we want. Now we simply need to switch the bottom grams into liters, which we can do that with the density of water because, again, this is such a dilute solution. Yes, it's toxic because it has cadmium in it, but the density is going to be about the same. So now we can say, well, 0.997 grams of water, or solution, is 1 milliliter of solution. Cancel it out, cancel it out. And we want liters of solution on the bottom, so I'm just going to get rid of that milli with a 10 to the negative 3. So let's see how we're doing here. I'm going to move that 10 to the negative 3 up top to make it positive. 10 to the 3 on top is going to cancel out 3 of the 10s on the bottom, so now I'm down to 10 to the 6th. 5 times 0.997 is basically the number 5. 5 times 1 is 5. So now I have 5 divided by 100. 100 would be 10 to the 2nd. This would be 10 to the 6th. So 2 powers of 10 extra would be basically 10 to the 8th. Or if I want to move that up top, 10 to the negative 8th. So I think the answer is pretty close to 5 times 10 to the negative 8th. Answer key agrees. Let's put that in the calculator. So I have 5 divided by 10 caret 6. Get an answer so that the exponent order of operation doesn't mess us up. Divide by 112.41 equals times 0.997 equals final answer. I get 4.4 times 10 to the negative 8th. As far as sig figs go, yeah, because 5 grams just has 1 sig fig, I should probably round that to 1 sig fig. So 4 times 10 to the negative 8th is the correct answer. So that's good to go. And then let's do our last problem, number 10. After these 10 problems, you should be an expert on this. So same problem here. Lethal dose is somewhere between 15 and 30 milligrams per kilogram of body weight. What is the concentration of these lethal doses in molality? And it says arsenic has a molar mass of 74.92 grams per mole. So we're looking at molality here. Just be careful, that's not molarity, but molality. So the units for that would be moles, in this case arsenic, per kilogram of solvent, and in this case the solvent would be the body. The body's dissolving the chemical. Alright, so we've got 2 problems set up here. Let's do the 15 and then we could just double the answer to get the 30 answer. So I've got 15 milligrams of arsenic per kilogram of body. Well, the nice thing about that is I'm already done with the bottom. That is the correct units for molality. Now I'm going to go from grams to moles, but the problem is this is in milligrams, so I'm going to cancel that with a 10 to the negative 3rd. Now using the molar mass straight from the periodic table, grams of arsenic to moles of arsenic. Periodic table says 74.92 per mole. Grams cancels, grams cancels. All right, so let's do some mental math here. We've got moles per kilogram. So 15 divided by 75. So 15 and 15 would be 60, plus another one would be 75. So yeah, this would be basically 1/3. 1/3, or 0.33 times 10 to the negative 2. Now, to make that a little bit more official, we would estimate, well, it's about 3 times 10 not to the negative 2, move it one more decimal place, times 10 to the negative 3. So I think this estimate is about 3 times 10 to the negative third. Oh, no, that is 10 to the negative third, so I should have put a 3 here. But yeah, because that's 10 to the negative third, I should have done negative third here, and then when I make it 3, that should be 10 to the negative fourth. Yeah, so I just missed one of my powers of 10 there. Answer key agrees with that. Let's get a real answer, though. 15 times 10 caret negative 3. Answer divided by 74.92. So sure enough, for this problem, 2 sig figs, 2.0 times 10 to the negative fourth. Perfect. So that is the answer for the 15 milligrams per kilogram. And then obviously this would be twice as big. So 4 times 10 to the negative fourth moles of arsenic per kilogram of body, which in this case is our solvent. That's what's dissolving. All right, so with that being said, I believe we've gone over all of these problems. So again, if you need some extra help, just let me know. Fractions are not going away, and every problem we pretty much solve the same way. What are we starting with? Where would we like to be at the end? And then it's simply some fraction conversions to get us from the beginning of the problem to the end.